Dear students, in today's class, let us discuss all the important equations related to chapter moving charges and magnetism. So this is one more chapter of second PUC, which is very important for all the competitive exams. Now, whenever current flows through a conductor, it produces magnetic field around it, and this effect is called magnetic effect of electric current. And the strength of this field can be measured using a law which is Biot-Savart's law, and this Biot-Savart's law gives the magnetic field due to a current element. So let's consider a conductor of any dimension, and you take small part of that conductor having length dl and let I with the current flowing through them. And if the product of I into dl is very small, so we call it as a current element. So at a distance r from the current element, the magnetic field is given by dB is equal to mu naught by 4 pi I dl sine theta by r square. Current through the current element, length of the current element, theta is the angle between the current element and the line joining the point to the current element. R is the distance of the point from the current element, and dB is the magnetic field. Mu naught is a constant called permeability of free space, which has a value of 4 pi into 10 power minus 7 Henry per meter. And since mu naught is 4 pi into 10 power minus 7, when you substitute here, the value of this constant mu naught by 4 pi is equal to 10 power minus 7 with the same unit. Now, magnetic field here is a vector, so therefore the same equation you can write in vector form. So vector dB is equal to mu naught by 4 pi into I, and here since we have sine theta, we are going to introduce a vector r, so that this becomes a r cube in the denominator, and we get the cross product, so that with the help of the cross product we can find the direction of the magnetic field. So when the current flows through this conductor, the magnetic field will be inward, and the direction of, we consider this a dl to be a vector, dl vector, and which will be in the direction of the current. And then we consider a position vector, which is here, it's a dl cross r, and that dl cross r will give you the direction of the field. So therefore here the vector that we write is dl cross r. So that is the vector form of the magnetic field due to a current element, and which is inward into the board. So this is the vector form. So this is how you get, if you write in magnitude, it will be dl r sine theta, dl r sine theta, and then divide by r cube. So that's how you get r square. So this is the equation using which we can find the strength of the field due to a current element. Now, by using this equation, we can find magnetic field produced by a current carrying conductor of different shapes. So starting with a straight conductor carrying current, I is the straight current carrying conductor, magnitude of the current is I, and at a perpendicular distance r, what is the strength of the field? To find this, first we have to join the ends of the conductor to that point, and then we have to measure two angles here. One is phi 1 and the other angle is phi 2. And based on this 4 variable, we get the field here as B is equal to mu naught by 4 pi mu naught by 4 pi r, and then into I, mu naught by 4 pi or mu naught I by 4 pi r into sine phi 1 plus sine phi 2. So this is the formula used to find the strength of the field at this particular point. Now if phi 1 is equal to phi 2, if both angles are same, that is when the point is exactly midway between this conductor. So then the field is given by B is equal to mu naught I by 4 pi r into phi. I'm going to consider this angle to be equal to phi. So therefore in that case it will be 2 sine phi. Now if the conductor is a very long straight conductor, a long straight conductor is one whose length is very large compared to the perpendicular distance. In that case, these angles phi 1 and phi 2 becomes very large. They are approximately 90 degree, and on substituting here sine 90 plus sine 90, you'll get the 2. So the strength of the field will be BC is equal to mu naught I by 2 pi r. So we use this modified version of the equation in the case of a long straight conductor, infinitely long straight conductor, and when the point is nearer to the midpoint or nearer to the center. If I have to find the field at one of its end, then BE is equal to mu naught I by 4 pi r. So that the ratio BC to BE will be equal to 2:1. The strength of the field will be more near the center and is exactly half at the end of the conductor. So we can use the same equation in finding the net magnetic field due to the various configurations. So I'm going to consider a square which carries current, and R is the side of the square. So what is the net magnetic field at the center of the square? Then we have a triangle whose side is R, and what is the net magnetic field at the centroid of an equilateral triangle carrying current I. So here each conductor produces the magnetic field, and then all the 4 conductors, when they produce the magnetic field and they will be in the same direction, will get added up to give net magnetic field. Similarly, we have the regular hexagon. So what is the magnetic field at the center of an hexagon whose side is equal to R? Now in all these 3 cases, the common factor which you have to remember is mu naught I by pi r is the common factor. B is equal to mu naught I by pi into r. B is equal to mu naught I by pi r is common in all the 3 cases. And in the case of a square, we get 2 root 2 times mu naught I by pi r. In the case of equilateral triangle, we get 9 by 2. And in the case of regular hexagon, we get root 3. So very easy to remember, special cases. So net field at the center of a square, at the centroid, and again at the center of a regular hexagon. By using Biot-Savart's law, we can even find the magnetic field due to a circular coil carrying current, where R is the radius of the coil and I is the current through the coil. At a point on the axis, at a distance x, the magnetic field is given by mu naught by 4 pi, 2 pi NIR square by R square plus X square to the power 3 by 2. N is the number of turns, I is the current, R is the radius, X is the distance of the point from the center. So, I am going to consider this is B suffix A, that is magnetic field at a point on the axis of a circular coil carrying current. Now, by substituting X is equal to 0, we get magnetic field at the center, which is BC is equal to mu naught by 4 pi 2 pi Ni by R. Now, the same thing can be written as a mu naught Ni by 2R. That's a simplified version, because this 2 pi and 4 pi, when we simplify here, we will get mu naught Ni by 2R. Now, that's the magnetic field at the center of the circular coil. So, we can write this ratio BA by BC. So, when you divide here, this mu naught by 4 pi and all that will get cancelled, and there is R square and this R is there, so that becomes R cube. Then divide by R square plus X square to the power 3 by 2. So, this will give you the ratio of the magnetic field at a point on the axis to a point at the center. Now, if X is equal to R, that is, if the point is at a distance equal to the radius, then you get this value of BA to be equal to BC by 2 root 2. Now, if X is equal to root 3R, then BA is equal to BC by 8, and then if X is a 2R, then BA is equal to BC by 5 root 5. So, these are the special cases one should remember, that relation between the magnetic field at a point on the axis to that at the center for the various distances. If I consider a circular coil carrying current of only one turn, then magnetic field at the center is mu naught I by 2R. Mu naught I, where N is 1, 2R. If I take a semicircular, that is half turn here, semicircular, then the field will be half of this. So, that will be BC is equal to mu naught I by 4R. If I take 1/4 of the circle carrying current, then the magnetic field at its center will be mu naught I by, again, half of the previous. So, that will be 8R. So, like this we can find the field due to the entire coil semicircular or 1/4. Now, what if an arc is given, then that arc subtends an angle theta at the center carrying current I, then the magnetic field BC is equal to mu naught I by 2R, that is magnetic field due to one turn, mu naught I by 2R, then into theta by 2 pi, this theta by 2 pi, and you have to make sure that angle theta will be in a radian. So, that will give you magnetic field at the center of an arc carrying current. So, what is a solenoid and a toroid? A solenoid is a cylindrical coil made up of a long wire which is wound uniformly, and when you pass current through the solenoid, it produces magnetic field at its center. So, a magnetic field at the center of a long solenoid carrying current is given by BC is equal to mu naught Ni, where N is the number of turns per unit length of the solenoid. Now, at its end, the field will be half of it. So, mu naught Ni by 2. So, that the ratio of the field at the center to that at its end will be 2:1. Now, this cylindrical coil, if you bend in the form of a ring, then you will get the toroid. So, the magnetic field at the center of the toroid at the center, in the sense at a point on its axis is given by, which is same as that of the solenoid, which is mu naught n I. But here n is number of turns per unit length, but it's bent in the form of a ring. So that's why it is n by, instead of L, that L becomes a 2 pi r, where r is the average radius of that entire ring or average radius of the toroid. So these are the two expressions which are important. One is magnetic field produced by a solenoid, and the other is the magnetic field that is produced by a toroid. And for a competitive exam, so they'll give some of the different configurations, and then you'll be asked to find what is the resultant magnetic field at a particular point of the given configuration. So let me give one such illustration where the configuration of this type is given. That is, we have two long straight conductors, one here and the other here, two. Okay, this is extended like this. And then we have a semicircular coil. And then we'll be asked to find what is the resultant magnetic field at this particular point or at the center of this particular arrangement. Now we have three parts here. One straight conductor, another straight conductor, the next is a semicircular coil. And we have to find three magnetic fields, and then based on the direction, we have to find the resultant magnetic field at that particular point. Now when we consider a straight conductor, the magnetic field at any point, along its length is always 0. Magnetic field at any point along its length is 0. You get field only around it, but not along the line where the conductor is present. So therefore, if you check this particular conductor, so this is the conductor, and the point, the center, this particular point, this lies along the length of it. Therefore, the field produced by this particular conductor is 0. Now, this is a straight conductor, and this is the end of the straight conductor, end. This is a straight conductor, this is the end of it. And this point is at a distance r. So what is the magnetic field at the end or at the ends of a long straight conductor carrying current, which is B is equal to mu naught I by 4 pi r. Near the center it is mu naught I by 2 pi r, but at the end it's mu naught I by 4 pi r. That's the magnetic field. Now what is the direction of the magnetic field? So you can find the direction of the magnetic field with the help of the right hand clasp rule. There are alternative rules also to find the direction of the current, and you can even find the direction like this. Suppose if the current in a conductor is in the clockwise direction, the current is clockwise. Okay, the current is clockwise, then the magnetic field will be inward direction, inward. And if the current is anti-clockwise direction, then the magnetic field is outward direction. Clockwise current, that's the current. Magnetic field will be inward. This is the direction of the magnetic field, inward. And if it is anti-clockwise, with respect to that point, then it is outward direction. And you can check here, the point is here. With respect to this point, you can see how the current flows here in this conductor. It's in the anti-clockwise direction. So it is anti-clockwise direction means it is outward. So therefore, magnetic field at this point due to this conductor will be outward. And that for the outward, the notation that is used is a dot like this. For inward, we use a notation cross. So magnetic field due to this conductor at this point is given by mu naught I by 4 pi r, and it is outward. Okay. So do remember this point. Clockwise, it's an inward direction, and then it's anti-clockwise means outward direction. Anti-clockwise current, outward direction is that of the magnetic field. Now, one more conductor is remaining. So due to this it's 0, due to this it's mu naught I by 4 pi r, and then due to the semicircle, due to this, it's a B is equal to mu naught I by 2r is due to one turn, one complete turn, it's 2r, mu naught I by 2r. But it's half, right? So half of it, so you'll get 4r. So this is the magnetic field due to this semicircle. Again, check the direction of the current with respect to this point. The current is flowing in anti-clockwise direction. No, can you see that? Anti-clockwise. If it is anti-clockwise, it's outward. So therefore, this magnetic field is also, it's outward. So we have found three fields. One field is 0, other field is this, other field is this. And now we have to find the resultant. What is the resultant of these three fields? This is anyways 0. And now you can see the two fields are along the same direction, outward and outward. So therefore, the resultant field is, for both the common is a mu naught I by 4r is common. Mu naught I by 4r is common. So mu naught I by 4r to this is 1 plus, here we have 1 by pi. So this is the resultant magnetic field at this particular point, and the direction of the net field will be outward. So this is how the arrangement will be given, where a configuration will be given and you will be asked to find the resultant magnetic field due to that particular configuration. So your job is to find the field due to the various parts of the conductor and then find the resultant using vector addition. So I'll give you one more configuration where we have a circular coil and the battery is connected in such a way that the current flowing through this branches into two parts like this. So now what is the resultant magnetic field at this particular point? Now if I is the current, since this part of the coil and this part of the coil, they are of the same length, the current divides equally. Now this, due to this part of the conductor, which is semicircular, the magnetic field is given by B is equal to mu naught, current is I by 2, divided by 2R. Now again, mu naught I by 2R is for one turn of the coil. For semicircular, divided by 2, it becomes 4R. The current is here clockwise. So clockwise means it's an inward direction, inward. The notation is a cross. This part of the conductor, it's a similar, exactly the same, right? Can you see that? So therefore, the field due to this part is B is equal to mu naught I by 2 by 4R. But see the direction of the current flows in the anti-clockwise direction. Clockwise inward, anti-clockwise it is outward. Now we have two fields which are exactly in opposite direction. They are equal in magnitude, opposite in direction, therefore the resultant is 0. So therefore the resultant magnetic field at this particular point is 0. So this is how the different configuration will be given, and there are many such diagrams. Do practice, they are all important diagrams, important question for the competitive exams. Now when current flows through a conductor, and if it is a closed loop of any shape, let me consider a circular shape, where I is the current through this loop and A is the area of the loop. A current carrying loop, it behaves like magnetic dipole. So this acts like magnetic dipole. If it acts like magnetic dipole, then one face of the coil behaves like south pole, the other face of the coil behaves like north pole. And here we can find that this face of the coil, it behaves like south pole, and exactly other side, other face of the coil behaves like north pole, so that this current carrying loop behaves like magnetic dipole. And magnetic moment of such magnetic dipole is given by M is equal to I into A. I is the current through the loop, A is the area of the loop. It is independent of the shape of the loop. But if there are a certain number of turns, then we can write M is equal to N I A. M is equal to N into IA. So that is how we can find magnetic moment. and it's a vector quantity. It is always directed from south pole to the north pole. It's a vector directed from south to north pole. Current into area. So ampere meter square is the SI unit of magnetic moment. Now, similar to this, a moving electron, when an electron revolves, in a circular orbit, it produces a current which is given by I is equal to Fe, or that's equal to E by T. So, a moving electron acts like a current loop, so that's why it produces a magnetic field as well as a magnetic moment, which we denote by mu suffix C. What is the magnetic moment of a revolving electron? It is given by E V R by 2. Charge of the electron, orbital velocity, radius of the orbit. That is also equal to E L by 2m, where L is the angular momentum of the electron. Okay, E V R by 2 or E L by 2m, where m is the mass of the electron and L is the angular momentum. So that is exclusively an equation to find the magnetic moment of an electron only. Now the ratio of the magnetic moment to that of the angular momentum is a constant, which is E by 2m. So E is charge of the electron and m is the mass of the electron. So therefore, for a given particle, this ratio will be a constant because charge is constant and mass is a constant. In electrostatic, so we have learned that when there is a electric field, and in that electric field, if there is a static charge, in an electric field, if you place a static charge, it experiences a force, electrostatic force, which is given by Q naught into E. Q naught into E. Similarly, if there is a magnetic field, in a magnetic field, if there is a moving charge, not static charge, moving charge, then it experiences a magnetic force which is given by F is equal to Q V B sine theta. So that is the symmetric nature of electric and magnetic field. In an electric field, if there is a static charge, it experiences the force called electrostatic force. Similarly, if there is a magnetic field and if you place, not exactly place, if there is a moving charge, then it experiences a magnetic force which is given by Q V B sine theta. So let's learn more about this magnetic force, and the magnitude of this force is given by F is equal to Q V B sine theta. What's the Q? Magnitude of the charge. What is the V? Velocity of the charge, moving charge. What is B? Magnetic field. What is theta? Is the angle between two vectors. One is a V vector, velocity vector, and the other is magnetic field vector. So you can write this equation in vector form. That's vector F is equal to Q into V cross B. V cross B. So if vector V is parallel to B, then the force is minimum. F minimum is 0. And if vector E is perpendicular to B, then the force is maximum, which is given by Q V B. And what do you mean by V perpendicular B? That's theta is 90 degree. What do you mean by V parallel to B? Theta is 0 degree. So if theta is 90 degree, then so definitely force is maximum, which is given by Q V B. And due to this force, the particle describes a circular path. And for the circular path, it requires a centripetal force, and that centripetal force is provided by the magnetic force. We can find the acceleration of it. A is equal to QEB by M. And when it describes circular path, the radius of the circular path R is given by P by BQ. P is a momentum, which is mv by BQ. That is also equal to root of 2mk by BQ. P is momentum, so which is mass into velocity. The same momentum can also be expressed in terms of the kinetic energy. So this is the radius of the circular path. And when it revolves in the circular path, we can find the time period of revolution, which is 2 pi m by BQ. We can find the frequency of revolution, which is BQ by 2 pi m, BQ by 2 pi m. And if you multiply 2 pi here, you will get omega, which is BQ by m. Omega means angular frequency of revolution. Now, when the particle moves in the circular path, the force is along the radius toward the center and the displacement is along the tangent. So, what is the angle between them? 90 degrees. Therefore, the work done is 0 because force is perpendicular to the displacement. W is equal to Fs cos theta, theta 90, so you will get W 0. And since work done is 0, there is no change in kinetic energy. Delta K is also 0. So, therefore, the particle moves in the circular path with the constant kinetic energy. There is no change in kinetic energy. And this principle is used in a device called cyclotron. In which the particles are accelerated with very high kinetic energy. And the frequency of revolution of the particle within the cyclotron is same as this. That's called cyclotron frequency, which is BQ by 2 pi m. BQ by 2 pi m. And maximum kinetic energy when the particle emerges out of the cyclotron is given by, it's a Q square B square R square by 2m. Q square B square R square by 2m. Charge, field, R. R is the maximum radius, or it is also called as the radius of the D inside the cyclotron, and m is the mass of the particle. So that is the expression for cyclotron frequency and the maximum kinetic energy of the particle accelerated inside the cyclotron. If the charged particle is allowed to move in a combined field, combined field means both electric as well as magnetic. Now, due to electric field, it experiences the electrostatic force, which is Q into E. Due to magnetic field, it experiences magnetic force, which is given by Q into V cross B. And the resultant force is the vector sum of both, which is F E and F B. So when you add them vectorially, Q is common, so you'll get Q into vector E plus V cross B. And this particular force, the net force, is called the Lorentz force. It's called Lorentz force. Suppose if the particle moves perpendicular to the electric field as well as the magnetic field. So this is V vector, this is E vector, and this is B vector. Okay. Then due to the electric field, it experiences a force in the upward direction. Due to magnetic field, it experiences a force in the downward direction, and if the net force is 0, if F net is 0, then the particle moves undeflected. It will not deviate its path, it will move straight, only if the net force is 0. And velocity of such particle is given by E by B. So this is the velocity of the undeflected particle moving in a combined field. It's also called as a crossed field. Crossed fields means perpendicular fields, electric field and magnetic field. So this equation is used to find the net force, and we use that here. And if F net is 0, then the particle, they move without any deviation with a velocity which is given by V is equal to E by B. So again, this principle is used in a device called mass spectrograph, which is used to find the mass of the elementary particles. If two charged particles Q1 and Q2, if they are separated by distance r, and if they move with a velocity v1 and v2, so there is electrostatic force between them, which is Fe is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. At the same time, there is a magnetic force as well, which is Fb. That is given by mu naught by 4 pi Q1 into Q2 V1 into V2 by r square. So this is the electrostatic force, this is the magnetic force, and the ratio of this, if you calculate Fe by Fb, Q1, Q2 will get cancelled here, r square will get cancelled, 4 pi will get cancelled, and you will get 1 by mu naught epsilon naught, and that's equal to c square. That's the speed of light, divided by V1 into V2. So this is a ratio of the electrostatic force and the magnetic force between two charged particles moving parallel to each other. In this case, you can see square of the speed of light is a very large value. So that's why electrostatic force is always much greater than the magnetic force because of this particular product. So electrostatic force is always dominating compared to the magnetic force between these two charged particles. So therefore here, if I take two like charged particles moving in the same direction, then due to the electrostatic force, the nature of the force is repulsive, plus. But since they move in the same direction, they will produce a current in the same direction, and due to the currents in the same direction, the nature of the force between them is attractive. So electrostatic force is repulsive, magnetic force is attractive. So what is the net force between the two charged particles, like charges moving in the same direction? As I mentioned, electrostatic force is much stronger than the magnetic force. The nature of the force is repulsive because the repulsive force is very large compared to the attractive magnetic force. So this is how we can find the electrostatic force as well as the magnetic force between two moving charged particles. If they are at rest, then there will be only electrostatic, there won't be any magnetic force between them. When a charge moves in a magnetic field with a velocity v, making an angle theta with the field, it experiences the magnetic force given by F is equal to Q V B sin theta. If there is a current carrying conductor of length L in a magnetic field which makes an angle theta, then it experiences the mechanical force which is given by F is equal to I L B sine theta. The vector form of this is vector F is equal to Q into V cross B. The vector form of this equation is vector F is equal to I into L cross B. The direction of the forces can be calculated using Fleming's left hand rule. So this is used to find the direction of the force, and this is used to find the force on positive charge. If it is a negative charge, then the direction of the force will be along minus F vector, means exactly opposite of vector F. Here also we have modified version of Fleming's left hand rule. So we have forefinger indicating the direction of the magnetic field. The middle finger indicates the direction of the velocity vector v, and then the thumb indicates the direction of the force on positively charged particle. Forefinger, magnetic field, middle finger indicates the direction of the velocity, and then the thumb indicates the direction of the force. So even here, the rule is almost the same. Forefinger indicates the direction of the magnetic field. The middle finger indicates the direction of the current here, okay, which is along the direction of, basically it's the direction of L vector that will be along the direction of the current. So the middle finger indicates the direction of the current, which is I. And then the thumb indicates the direction of the mechanical force on the conductor. So that's the comparison. Again, both are very important. And if the charged particle moves parallel to the field, zero force. If the current carrying conductor is parallel to the field, zero force. If the particle moves perpendicular to the field, maximum force. If the conductor is perpendicular to the magnetic field, again the force is maximum. By using mechanical force experienced by a current carrying conductor, we can even find the force between two long straight parallel conductors carrying current, which is given by F is equal to mu naught I1 I2 by 2 pi r, where r is the separation between the two conductors and I1 I2 current through both. Now force is force is attractive if they carry current or currents in same direction. If they carry current in same direction. The force is repulsive if they carry currents in opposite direction. If they carry currents in opposite direction. So if the force is attractive if they carry currents in same direction, and the force is repulsive if they carry currents in opposite direction. And this is the formula used to find the force between two long straight conductors carrying current. If you want to find the force on finite length of the conductor, then multiply this by L. F is equal to mu naught I1 I2 by 2 pi r into multiply by length of the conductor. You will get the total force on a conductor having certain length. And that's why the unit of force here is not Newton here, it's a Newton per meter, because we are finding force per unit length. But in this case, the unit is Newton only, because we are finding the total force on a given length of the conductor. So when a current carrying loop is placed in a magnetic field of again any shape, it experiences a torque which is given by tau is equal to mb sine theta, or the vector form is equal to vector tau is equal to m cross b. if the plane of the coil is parallel to the magnetic field, if the plane of the coil is parallel to the magnetic field, this direction of m vector is along the normal, that is perpendicular to the plane of the coil. Coil is parallel to the field, whereas magnetic moment is perpendicular. So that what is the angle between the two vectors m and b? It's a 90. So now the torque is maximum. Tau is maximum. If the coil is placed in such a way that the plane of the coil is perpendicular to the field, whereas magnetic moment is parallel to the field. So angle between the two vectors is 0, sine 0 is 0, so therefore in this case the torque is minimum torque, which is 0. So torque is maximum if the plane of the coil is in the direction of the magnetic field. The torque is minimum when the plane of the coil is perpendicular to the magnetic field. And this principle is used in a device called galvanometer. And in the case of a galvanometer, we can measure 3 variables. One is potential difference required for full scale deflection, Vg. Ig, current required for full scale deflection. And capital G is the resistance of the galvanometer. And we can always convert a galvanometer into an ammeter. We can convert a voltmeter into ammeter, and then we can increase the range of the ammeter. We can convert galvanometer to ammeter, we can convert voltmeter to ammeter, we can increase the range of the ammeter. This is not conversion, this is increasing the range. What do you mean increasing the range? So there is an ammeter having range 0 to 2 ampere. So maximum current that we can measure is 2 ampere. But I want to increase the range so that we can measure a current of up till 20 ampere. So 0 to 2 ampere, we can increase to 0 to 20 ampere. That is the meaning of increasing the range. And for all these 3 changes, galvanometer to ammeter, voltmeter to ammeter, increasing the range of the ammeter, we have to connect a low resistance in parallel. In the next type of conversion, where we can convert a galvanometer to voltmeter, we can convert ammeter to voltmeter, and then we can even increase the range of the voltmeter. And we can do this conversion by connecting a high resistance in series. So what is the value of that low resistance? The low resistance is given by S is equal to IgG by I minus Ig. IgG is those variable, current required for full scale deflection, and G is the resistance of the galvanometer. And what is I? I is the maximum current to be measured. Maximum current to be measured. So what is the high resistance to be connected in series, which is R is equal to V by Ig minus G, where V is the maximum potential difference to be measured. Maximum potential difference to be measured. Now to increase the range of an ammeter, we have a shortcut equation, which is S is equal to G by n minus 1, whereas here R is equal to n minus 1 into G. Now what does this n stands for? N stands for the ratio of the new range to the initial range. For example, I had given here, just now, 0 to 2 ampere to 0 to 20 ampere. So 20 ampere is my new range. 2 ampere is my initial range. 20 by 2, 10. So the value of n is 10. So that is that value of n. And what is G? G is the resistance of that given ammeter. This ammeter has certain resistance, right? So that is the value of G. So therefore, this is the shortcut used only for the last changes or for last modification. Okay. If we want to increase the range of the ammeter, what is the resistance required? A low resistance in parallel having value this. If you want to increase the range of an voltmeter, then you have to connect high resistance in series given by this particular formula. Where n still remains the same, it's the new range to the initial range. So now let's learn all about another source of magnetic field, which is a bar magnet. So when we consider a bar magnet, it has 2 points within where the entire field is assumed to be concentrated, and we call that as the south and the north pole. And separation between them is taken as a 2L, which is called magnetic length. And this magnet has a magnetic moment which is given by M. That's equal to Qm into 2L. Qm is a pole strength and 2L is the magnetic length. And Qm has a unit ampere meter and again into meter, so that will give you ampere meter square, which is same as the magnetic moment produced by a current loop. At a point on the axis and at a point on the perpendicular bisector. So what is the magnetic field at a point on the axis? It is mu naught by 4 pi 2 mr by r square minus l square, the whole square. This is similar to the electric field produced at a point on the axis of a electric dipole. Similarly, the magnetic field at a point on the perpendicular bisector, okay, which are at equatorial line, that's equal to mu naught by 4 pi, mu naught by 4 pi. M by r square plus l square to the power 3 by 2. If it is a short magnetic dipole, then the field at a point on the axis is mu naught by 4 pi. It's a 2m by r cube. Whereas the field at a point on the equatorial line, mu naught by 4 pi m by r cube. And this ratio, field at a point on the axis to that at a point on the equatorial line is 2:1. When this magnet is placed in a magnetic field, it experiences the torque given by tau is equal to mb sin theta. And when placed in a magnetic field, to rotate the magnet, so we have to do the work, and that work done is given by mb into cos theta 1 minus cos theta 2. So these are all identical equations which we have already discussed in electrostatic. So what is theta 1, theta 2? So theta 1 is the initial position of the magnet with respect to the magnetic field, or it is the angle between magnetic field and dipole moment, when it is oriented by an angle theta 1. From that theta 1, if I want to rotate it further by an angle theta 2, then that is the expression which is used. Work done to rotate the magnet which is in a magnetic field from one position to another position is given by this equation. Suppose if the magnet is initially in the equilibrium position, it's aligned in the direction of the field. Then from that, if I have to rotate by an angle theta, then the work done is given by W is equal to mb into 1 minus cos theta. And as we rotate, we do work, and that's stored as energy, which is given by U is equal to minus mb cos theta. So this is the magnetic potential energy stored in a magnet when it is rotated through an angle theta. So these are the equations related to magnet. And when a magnet is suspended in a magnetic field and it is deflected by a very small angle, and if it is allowed to oscillate, then the time period of such oscillating magnet is given by T is equal to 2 pi root of I by mb, where m is the magnetic moment, b is the magnetic field, and I is not the current here, I is the moment of inertia, which is given by m L square by 12. So there are two m, this is magnetic moment, this is mass of the magnet, length of the magnet, magnetic field, and I is the moment of inertia of the magnet. The frequency of oscillation, f is equal to 2 pi inverse of it, root of m b by I. So this is the frequency of oscillation of a magnet when placed in a magnetic field. Terrestrial magnetism, that is magnetism produced by the earth. So earth behaves like a huge magnet with one end of it behaves like magnetic north and the other end magnetic south. And these are called magnetic poles, which are completely different from the geographic poles, So this is the near magnetic north we have geographic south, and near magnetic south we have geographic north. So basically this is the geographic north and this is the geographic south. Now very important here, near geographic north we have a magnetic pole which behaves like south pole, magnetic south. But since it lies in the northern hemisphere, it is named as magnetic north. So listen carefully. Near the geographic north we have a magnetic pole. By property it is a south, no doubt it is a south pole. Property wise it acts as a magnetic south. But while naming, it's named as magnetic north pole because it lies in the northern hemisphere. Similarly, near geographic south we have a magnetic pole. By property, by nature, it is a north pole, magnetic north of the earth, but while naming, it is named as magnetic south pole. So that is the reason why this is the kind of diagram that you get to see in the NCERT, where they have given geographic north and it's given as magnetic north, but by nature this is the south pole, but while naming they have named it as exactly opposite just because of the location, understood? Geographic location, it is named as a magnetic north. Now the plane passing through the geographic poles is called as geographic meridian. The plane passing through the magnetic north, magnetic poles is called as magnetic meridian, and the angle between them is called declination. So delta is the declination, which is the angle between the magnetic meridian and geographic meridian. Suppose if you consider this is the magnetic meridian, the plane passing through the poles. So the magnetic field lies in this plane, that is the magnetic south. So let us consider this is the direction of the Earth's field at a place, which makes an angle theta with the horizontal. So if a magnet is made to oscillate in a vertical plane, then the needle will get inclined like this. This is how the needle will stand. That is, the axis of rotation is a horizontal. And when the needle is getting inclined like this, it remains inclined with an angle theta with the horizontal. So that's why this particular angle is called as inclination, or is also called as a dip. This is a declination. This is inclination. If this is B and if this is theta, the component of that will be B cos theta along the horizontal. That's what is called as horizontal component. BH is equal to B cos theta. Along the vertical, it's vertical component BV, that's equal to B sin theta. So what is the relation between the total field and the horizontal component? So B is equal to root of BV square plus BH square. And the ratio of BV by BH. BV by BH will give you tan theta. So theta is called dip or inclination, and here delta is called declination. So declination is the angle between the two meridians, whereas the inclination or the dip is the angle made by the Earth's field, total field, with the horizontal in magnetic meridian, in magnetic meridian. So that is called as the inclination or the dip. So now let us learn all the terms that's associated with magnetic material. So what are magnetic material? Material that can be magnetized are called magnetic material. When we use a solenoid, and if N is the number of turns per unit length of a solenoid, and if I is the current flowing through the solenoid, then product of this number of turns per unit length and current is called magnetic intensity. Magnetic intensity, which is denoted by H, and it's given by the product of number of turns per unit length into the current. So that's why the unit is ampere meter. And this is independent of the medium that is present, inside the solenoid. It doesn't depend on the medium that is used. Now, when we place any material to magnetize it, then all the magnetic dipole inside the material, they get aligned due to this field, due to the magnetic intensity, and the net magnetic moment acquired per unit volume is called as magnetization, which is M. So magnetization is net magnetic moment acquired per unit volume of the magnetic material, and the unit of magnetic moment here is ampere meter square. So unit of H is ampere per meter here, okay, not ampere meter, because it's a number of turns per unit length. So that's what is ampere per meter. Okay. So net magnetic moment is ampere meter square by meter cube. So the unit is ampere per meter. So the unit of the magnetic intensity and unit of magnetization, both are same. So these are the pair of quantities having the same dimensional formula. Now, greater the magnetization, greater is the magnetic field, that is produced by such material. And the material that can be easily magnetized are iron, and or we call it as a ferromagnetic material. In such material, the magnetization attained is very high. So therefore, the degree of magnetization depends on the quantity, which is M. And the ratio of magnetization to that of the magnetic intensity is denoted by a Greek alphabet, which is chi, and it's called magnetic susceptibility, which has no unit. And magnetic susceptibility is a measure of the ease with which a material can be magnetized. Based on the magnetization that is attained, magnetic materials are classified into three substances. One, diamagnetic substances, paramagnetic substances, and then ferromagnetic substances. Diamagnetic substances are one in which materials are very weakly magnetized in the direction of, in a direction opposite to that of H. A paramagnetic substance is one in which the materials are weakly magnetized, in the direction of H. Whereas ferromagnetic substances are one in which the materials are strongly magnetized in the direction of H. So the difference between the dia and the para, both are weakly magnetized, but the direction of magnetization is different. The difference between para and ferromagnetic substances are the direction of magnetization is same, but one is weakly magnetized, the other is strongly magnetized. And for out of these three material, the susceptibility is chi, is a low and negative for diamagnetic substance. Low because it's a weakly magnetized, negative because it is magnetized in a direction opposite to that of H. For paramagnetic substance, it's a low and positive. And for ferro, it is high and positive. Low because it's a weakly magnetized, positive because it's magnetized in the direction of H. In the case of ferromagnetic substance, again it's strongly magnetized, that's why susceptibility is high, and positive because it's magnetized in the direction of H. Ability of the material to allow magnetic lines of force is measured by magnetic permeability, which is mu. So mu is equal to B by H, whereas chi is equal to M by H. The net magnetic field B is given by mu naught into M plus H, where H is magnetic intensity and M is magnetization. And based on this relation, we get mu is equal to mu naught into 1 plus chi. And mu by mu naught is nothing but mu r, which is a relative permeability, is equal to 1 plus susceptibility. So mu means magnetic permeability of the medium, mu r means relative permeability of the medium, and mu naught is permeability of free space. So these are the different relation between the different physical quantities associated with the magnetic material. And one of the law which is applicable to paramagnetic substance is susceptibility, is inversely proportional to the absolute temperature, and this particular law is called Curie Law, and it's exclusively applicable for paramagnetic substance only, because in the case of diamagnetic substance, susceptibility is independent of the temperature, it doesn't depend on the temperature. So these are the important equations of an important chapter, moving charges and magnetism and matter. So number of questions they ask, especially from this particular these two chapters. So important to go through these equations, read, revise, then you'll be able to solve many questions. Thank you.